Let's talk about colligative properties. By definition, colligative properties are properties that depend only on the amount of solute present in solution. The identity of the solute, as it turns out, however, doesn't really matter, but the amount of that solute does matter. And if the solute happens to split up into multiple parts, like in the case of an ionic salt, where it splits into cation and anion, then each one of those components counts as a single solute, so you have to count the whole thing. And that total amount will affect the property of the solution, whether it is the vapor pressure, uh, maybe boiling points, even melting points, um, will be affected for the solution just by having the solute. So you may remember when we talked about the idea of vapor pressure, liquids have a tendency to evaporate to some extent, creating a vapor pressure. And that's what we call basically the vapor pressure. And we talked about the Clausius-Clapeyron equation. We talked about how this relates to intermolecular forces. And when you start thinking about solutions, the question becomes, well, what is the solute doing along the solvent that surrounds it? And the idea is that the solute is dissolving in your solvent because there are some intermolecular forces of attraction that are very much attractive between solute and solvent. And so the act of dissolving a solute in a solvent is a means for you to increase the overall number of intermolecular forces of attraction present in your sample. So what you're basically doing is making it harder for your solvent molecules to break apart from the bulk sample and go into the gas phase. So you actually, instead of having this many solvent particles turn into the gas phase, now you have less. So you basically decrease the vapor pressure by adding solutes to your solvent. And this is fully an intermolecular force of attraction argument. Now the solute need not be a fully covalent molecule. You could have an ionic salt, like lithium chloride, in which case the lithium chloride splits up into lithium plus and chloride minus. So technically for every lithium chloride you have, you're actually ending up with two equivalent solute particles present in solution. And here is where you create your ion dipole forces. For lithium, you have the negative end of the um, alcohol molecule shown in here, and that faces the cationic portion, the lithium plus portion of the dissolved salt. And together that kind of keeps the solvent um, in the bulk sample as a result of the increased intermolecular forces of attraction, thus lowering the amount of liquid turning into gas. So as I was mentioning before, the total number of ions will need to be accounted. In some cases, it will be accounted in the formulas that we're going to be looking into. In other cases, we have to account for the total amount of ions after the fact. So keeping in mind, your long dispersion forces, your dipole-dipole forces, hydrogen bonding, ion dipole, that's going to be pretty important for the premise of the colligative properties. And as I was describing right here, volatility will also play a big role. In fact, the first colligative property we'll look into will involve everything in regards to volatility, the vapor pressure of the sample. So these solute-solvent interactions, which lead to similar or stronger intermolecular forces, ultimately make it harder for the solvent to break away into the gas phase, which means either of two things. First, the vapor pressure of that liquid is going to be lower, and two, because it's harder to turn the liquid into gas, the boiling point will also be higher. So we have all these similar physical traits that get affected just by having the solute present in solution. So increase the intermolecular forces, increase the amount of energy needed to break the interaction, increase intermolecular forces, decrease the volatility. This is what this is being said. And as I just stated, increase intermolecular forces will mean that you will also increase the boiling point of the solution. So the colligative properties come in four forms. The first one is known as Rolle's law, which involves calculating the vapor pressure of the solution based on the vapor pressure of the pure solvent. But notice here that the vapor pressure of pure solvent is being multiplied by the mole fraction of the solvent, meaning that as you have more solute and more solute and more solute in solution, the quantity of solvent or the ratio of solvent to solute is going to start decreasing, decreasing, and decreasing, meaning that your vapor pressure solution will also go down. Then we have the boiling point elevation formula, where we determine by how much does the boiling point change upon having some molality of solute present. And in this formula, we actually have the symbol I, which represents the number of ions present in solution. And if the molecule happens to be completely molecular or covalent, then the value of I is automatically 1. But for ionic substances that do dissolve, you need to count how many ions they have present, and that will have to be the value of I. Similarly speaking, the freezing point depression formula has pretty much the same overall format, except that instead of using the boiling point elevation constant, we use the freezing point depression constant. The number of ions still needs to be counted. You still work with molality, but this time you look at how the melting point temperature or the freezing temperature goes down as a result of having solute in it. And the last one is known as the osmotic pressure, which tells you how a substance, a solution, when presented with a permeable membrane in which a similar solution is present on the other side of the membrane but of different concentration, how much pressure you create as a result of that differential concentration across the membrane. Here you also account for a number of ions. So notice that out of the four formulas, the boiling point elevation, freezing point depression, and osmotic pressure account for a number of ions in them within the formula. Rolle's law does not, so here you definitely have to account for that during your calculations. I'll show you what I mean when we do some examples. So let's stop right here, and on the next video let's talk about Rolle's law.